Welcome everybody once again. So this is our 10th class for module 2. In the last class we see what is continuity equation, and we saw the continuity equation is rho 1 a1 v1 is equal to rho 2 a2 v2. So this is nothing but the mass, right? So mass at one section is equal to mass at the second section. That was the continuity equation. Now let us see the continuity equation in 2 and 3 dimensions. So for that we are considering a fluid element of lengths dx, dy and dz in x, y and z directions. So listen, so this is our fluid element. This is our fluid element. So this fluid element is of length dx. So in x direction, the length of this fluid element is dx. In y direction, the length is dy. So this direction it is dy, and in z direction the length is dz. So here the length is dz. Now let u, v and w be the inlet velocity components in x, y and z directions respectively. So we will mark the directions. So this is our x direction. This is the x direction of our fluid element. So x direction. This is our y direction. And this is our z direction. Okay, so in x direction, the velocity is taken as u. The velocity in x direction, that is the velocity component is in x direction, is assumed as u. The velocity in y direction is assumed as v, and the velocity in z direction is assumed as w. So if this is the case, okay, the mass of the fluid, let us mark the phases. So this phase is A, this is B, C, D. So this is one phase. A, B, C, D is one phase, and the another phase is E, F, G, H. So this will be our E, F, G and H. So we have two phases A, B, C, D and E, F, G, H. So mass of the fluid. So the fluid is flowing in this direction. This is how the fluid is flowing. So when the fluid is flowing, the mass of the fluid entering the phase A, B, C, D, that will be equal to, we know our continuity equation is rho AB, density into area into velocity. So that means it is density, that is mass of the fluid entering the phase A, B, C, D will be equal to density of the fluid entering the phase A, B, C, D multiplied by the velocity of the fluid in x direction, because the flow is in x direction. So velocity in x direction multiplied by area of phase A, B, C, D. Okay, so it is rho into velocity in x direction is taken as u. So it is u, area of a phase ABCD. See, for this phase ABCD, the area is dy into dz. For this phase, it is dy into dz. Okay, the area is dy into dz. So it is dy into dz. This is the area of the phase ABCD. Now, so if the fluid is entering through the phase ABCD, it should leave through the phase EFGH. So what will be the mass of a fluid leaving the phase EFGH? That will be equal to, see, this mass, that is mass entering in the phase ABCD, plus see there is a space in between this phase ABCD and EFGH. So when there is a space in between these two phases, there will be a difference in mass. Okay, difference in mass in x direction. So that is dou by dou x of. So this is our mass, right? Dou rho u dy dz is the mass of the fluid entering the phase. So the differentiation of this mass. So the mass of the fluid entering this phase plus the change in mass when the fluid is flowing from one phase to the another phase. So in x direction. So it is dou by dou x of the mass into dx. So now we will take this, that is the mass of the fluid entering the phase, we will take it as equation number 1, and mass of the fluid leaving the phase EFGH, we will take it as equation number 2. So if this is the case, the gain in mass, see there is a gain in mass. Okay, so how much mass is gained? So that will be equal to 2 minus 1. So 2 minus 1, when you subtract this 2 minus 1, so these both will get cancelled. The only thing remaining is dou by dou x of rho u dy dz into dx. So this is the gain of mass in x direction. So if this is the gain of mass in x direction, gain of mass same way in y direction, the gain of mass will be equal to dou by dou y of rho v. U is the velocity in x direction, v is the velocity in y direction, velocity component in y direction, into dx dy dz. Similarly, gain of mass in z direction will be equal to dou by dou z of rho into omega w. W is the velocity component in z direction, into dx dy dz. So your net gain of mass, that is, see, this is three-dimensional flow. Your fluid component is a three-dimensional component. You have x direction, y direction, and z direction. So it is a three component. So for this three component, the total gain of mass, net gain of mass will be equal to, we add all these three. Add the gain of mass in x direction, gain of mass in y direction, and gain of mass in z direction. So when you add, see, dx dy dz is common for all the three directions. Dx dy dz, you have dx dy dz and dx dy dz. So we take this dx dy dz common. The remaining thing is dou by dou x of rho u plus dou by dou y of rho v plus dou by dou z of rho w. Now, see the mass, when you look into the diagram, the mass entering through the phase ABCD is leaving through the phase EFGH. So there is no accumulation, there is no stagnant of water, there is no stagnant of flow. Okay, it is flowing. So when it flows, there is no accumulation of the mass. That means the net gain of mass will be equal to 0. Okay, there is no accumulation of mass, which means net gain of mass is equal to 0. So if net gain of mass is equal to 0, this equation, that is the total, that is net gain of mass, this equation is equal to 0. So if this equation is equal to 0, this equation becomes a 0. So you take this, you cross multiply. So you get dou by dou x of rho u plus dou by dou y of rho v plus dou by dou z of rho w is equal to 0. Okay. So that is what is written here. Dou by dou x of rho u plus dou by dou y of rho v plus dou by dou z of rho w is equal to 0. Now, we know if the fluid is compressible, that is for liquids, the density is constant. So if density is constant, you can cancel this density everywhere. What we get is dou u by dou x plus dou v by dou y plus dou w by dou z is equal to 0. This is your continuity equation in three-dimensional fluid flow. This is your continuity equation. Continuity equation in three-dimensional fluid flow. Dou u by dou x. It is related with respect to the velocity components. Velocity in x direction, velocity in y direction, velocity component in z direction. So dou u by dou x plus dou v by dou y plus dou w by dou z is equal to 0. This is for 3 dimension. So what happens if it is for 2 dimension? So this equation becomes dou u by dou x for 2-dimensional flow. This equation becomes dou u by dou x plus dou v by dou y is equal to 0. This is our continuity equation for 2-dimensional flow. So in general, while the fluid is flowing through a pipe, the continuity equation is, when you are taking two sections, the continuity equation is, it is law of conservation of mass, right? Mass remains the same. That means your rho1, V1, A1 will be equal to rho2, V2, A2. Now, when the flow is 3-dimension, our continuity equation is dou u by dou x plus dou v by dou y plus dou w by dou z is equal to 0, and for 2-dimension it is dou u by dou x plus dou v by dou y is equal to 0. Very, very important derivation. Okay, simple and important derivation. Now we will move on to our next next topic today, that is velocity and acceleration. Very simple concept. So suppose v is our resultant velocity. We know velocity is a component is a function of u, v and w in space. That is, in space means in terms of direction, that is x direction, y direction and z direction. And this also will be a function of time t. If this is the case, if v is the resultant velocity at any point in a fluid flow, let u, v and w be the velocity components in x, y and z direction. And these u, v and w will be a function of x, y, z and time. Okay, so if this is the case, our u will be equal to velocity component in x direction. U will be a function in x, y, z and t. V will be a function of x, y, z and t. W will be a function of x, y, z and t. That means our v is equal to, v can be written in terms of vector. That is u into I vector plus v into j vector plus w into k vector. U is the velocity component in x direction, v is the velocity component in y direction and w is the velocity component in z direction. So the magnitude will be equal to square root of u square plus v square plus w square. Similarly, see these concepts I think you have studied in your engineering mechanics also. Similarly, the acceleration. So ax, ay, az be the acceleration components in x, y and z direction. If so, your ax will be equal to, we know acceleration is differentiation of velocity with respect to time. So du by dt. So you get u into dou u by dou x, because u is a function of x, y, z and t. So ax is equal to du by dt. You get u into dou u by dou x plus v into dou u by dou y plus w into dou u by dou z plus dou u by dou t. Similarly, our ay will be equal to dv by dt. So here you see it is dou x, dou y, dou z, dou t, and here it is u. Okay, only this u. Now for ay it is v. So everywhere in the numerator you will have v. The denominator, it is a function of x, y, z and t. So dv by dt is equal to u into dou v by dou x plus v into dou v by dou y plus w into dou v by dou z plus dou v by dou t. Similarly, our az is equal to dw by dt. That we get dou w by dou x plus dou w by dou y plus dou w by dou z plus dou w by dou t. See, now we have three acceleration components, ay, ax, ay, az. So our acceleration can be written as a is equal to ax into I vector plus ay into j vector plus az into k vector, and the magnitude of acceleration is equal to square root of ax square plus ay square plus az square. You will get the magnitude units. Okay. Now, for steady flow, we have already studied the types of fluid flow. So, steady flow and unsteady flow. For steady flow, the velocity, differentiation of velocity with respect to time is equal to 0. So, if the flow is steady, this term becomes 0. This term becomes 0. You will have only the remaining terms if the flow is steady. Now, we will see what is local acceleration and what is conventional acceleration. Okay, so local acceleration and convective acceleration. So local acceleration means, see, in this acceleration, we have acceleration components ax, ay and az. In these components, that is differentiation of velocity components with respect to time. These are called local acceleration. That is differentiation of velocity with respect to time. Differentiation of velocity components with respect to time is called local acceleration, and all the remaining acceleration is called, that is these things. That is dou u by dou x, dou u by dou y, dou u by dou z, dou v by dou x, dou v by dou y, dou v by dou z. These terms. Oh, I forgot to. See, here it is u into v into w into. Okay. Please write that. I forgot to tell it. Just I missed it here. I will try to write u, v, plus w into. Okay. Okay, so these are called convective acceleration. That is differentiation of velocity with respect to the space or the direction. That is called convective acceleration. Okay. So see, local acceleration is defined as the rate of increase of velocity with respect to time. With respect to time at a given point in a flow fluid. That is dou u by dou t, dou v by dou t and dou w by dou t are known as local acceleration. Whereas convective acceleration is defined as the rate of change of velocity due to the change of position. That is change in space of fluid particles in a fluid flow. So all the remaining accelerations, differentiation of velocity with respect to the spatial components are called convective acceleration. Okay, you can see these are the differentiation of velocity components with respect to the directions, with respect to the space. Now, with this understanding, we will move on to a problem. We will see one problem today. Remaining problems we will see in the next class. A simple problem. So, it is given the velocity vector in a fluid flow is given as v equal to 4x cube into I vector minus 10x square y into j vector plus 2t into k vector. Find the velocity and acceleration of the fluid particle at 2, 1, 3 at time t is equal to 1. So, we know our velocity is a function of, x, y, z and t. Right? So, here x is given as 2. X is given as 2, y is taken as 1, z is taken as 3. That is the spatial components. This is the spatial components. X is 2, y is 1, z is 3. This is the time component. T is equal to 1. Now, see, velocity is given as, velocity vector is given as 4x cube into I vector minus 10x square y into j vector plus 2t into k vector. That means this is u into I vector. This minus 10x square y is v and 2t is w. Because v is equal to u into I vector plus v into j vector plus w into k vector. Okay, so this is our u. 4x cube is u, Minus 10x square y is v and 2t is w. Now, okay, so u is 4x cube. We substitute x is equal to 2. This x is equal to 2. So, we get u equal to 32 units. Similarly, v is equal to minus 10x square y. Substitute x is equal to 2 and y is equal to 1. We get v is equal to minus 40 units. W is equal to 2t. W is equal to 2t. Substitute t is equal to 1. We get 2 units. Now, the velocity is given as. So, u into I vector. We will write the velocity v is equal to u into I vector plus v into j vector plus w into k vector. So, u is 32. So, 32 into I minus v is 40 plus v is minus 40. So, minus 40 into j. W is 2. So, it is plus 2 into k or vector. You can put vector also. Okay, so this is important. Your velocity component, velocity vector is very important. Okay, velocity vector. After this, we will find the magnitude. So, magnitude is equal to square root of 32 square plus minus 40 the whole square plus 2 square. We get it as 51.26 units. Now, we will move on to the acceleration. Similarly, we know acceleration is equal to acceleration ax is equal to differentiation of u with respect to t. So, what we get is u into dou u by dou x plus v into dou u by dou y plus w into dou u by dou z plus dou u by dou t. This is acceleration component in x direction. Okay. The reason is u is a function of x, y, z and t. That is why it is ax is equal to u into dou u by dou x, function of differentiation of dou u by dou x, dou u by dou y, dou u by dou z and dou u by dou t, because it is a function of x, y, z and t. Now, we have already found what is u, v, w is already found. U is 32, v is minus 40, w is 2. Now, for dou u by dou x, you substitute dou by dou x of u. Our u is 4x cube. U is 4x cube. Only then we can differentiate. Okay. So, everywhere dou by dou x of u is 4x cube. Dou by dou y of u is 4x cube. Dou by dou z of u, that is 4x cube. Dou by dou t of 4x cube. So, differentiating with respect to x, that is 32 into 4x cube. Differentiation, we get 12x square. So, it is 12x square. Here, there is no y term. So, the differentiation of this becomes 0 with respect to y. There is no z term. So, this becomes 0. There is no t term. So, differentiation with respect to t becomes 0. So, we get 32 into 12x square. This 32 into 12 into x is given as 2. So, 2 square. We get 1536 units. Similarly, ay will be equal to u into dou v by dou x plus v into dou v by dou y plus w into dou v by dou z plus dou v by dou t. So, u we have already determined it as 32 into dou by dou x of v. V is minus 10x square y plus v we have already found it as minus 40 into dou by dou y of this v is again minus 10 square y plus 2 into, that is w is 2 into dou by dou z of, this is v minus 10x square y plus dou by dou t of v is minus 10x square y. Now, we are differentiating with respect to x. So, we get 32 into, when we differentiate it with respect to x, we get minus 10, y is constant. So, for x square, it is 2x. So, we get 32 into minus 20xy. Okay, it's 32 into minus 20xy. Now, minus 40 into, differentiate with respect to y, we get minus 40 into, so minus 10x square is constant. Differentiation of y is with respect to y is 1. So we get minus 40 into minus 10x square. Here with respect to z, we don't have z term, so this becomes a 0. Now with respect to t, we don't have t term, so this becomes a 0. So substituting, we get 32 into minus 40. Because 20x, the value of x is 2, right? Value of x is 2. So it is minus x is 2, so it is, and y is 1. X is 2, y is 1. So we get minus 40. Minus 40 into, again, minus 10 into x is 2. So 2 square, we get minus 40. So it is substituting, we get minus 40 into 32 minus 40. It is minus 40 into minus 8. We get 320 units, positive, 320 units. Similarly, AZ is equal to U into dou W by dou X plus V into dou W by dou Y plus W into dou W by dou Z plus dou W by dou T. So U is 32, dou by dou X of W is 2T plus V is minus 40 into dou by dou Y of W is 2T plus W is 2, dou by dou Z of W is 2T plus dou by dou T of 2T. So now differentiating with respect to X, there is no X term, so this becomes a 0. Now differentiating with respect to Y, we don't have Y term, so this becomes a 0. Differentiation with respect to Z, there is no Z term, so this becomes a 0. So dou by dou T of 2T, differentiation of 2T is 2. So it is 2 units. Now we have Ax, Ay and Az. So our acceleration will be equal to Ax into I vector plus Ay into j vector plus Az into k vector. So substitute Ax, Ay, Az. Ax is 1536, Ay is 320 units and Az is 2. So our magnitude of acceleration becomes square root of, this answer is very important, okay? Very important for exam point of view. Acceleration will be equal to 1536 square plus 320 square plus 2 square. We get 1568.9 units. So thank you. Only one problem for today. Remaining problems and the next concept we will see in the next class. Thank you.